Welcome to my channel. Imagine standing at the edge of a vast, dark ocean. But this isn't water stretching before you. It's rubber. Mountains of discarded tires, piled so high they block out the horizon. Every single year, our world throws away more than 1.5 billion tires. That's not a typo. 1.5 billion. Each of these tires will sit in our environment for up to 4,000 years, barely decomposing, slowly leaching toxic chemicals into the soil and groundwater below. For decades, this made tires one of the most notorious forms of waste on our planet. So toxic, so persistent, they were rejected almost everywhere. But today, something extraordinary is happening. That very same waste, once considered worthless, is now being actively sought after by engineers around the world. It's being treated as black gold. The key ingredient in a revolution that's transforming how we build our roads. This is the story of rebirth. The complete transformation of a single tire, from the moment it's discarded to its fusion with hot asphalt, creating road surfaces with exceptional durability. A material once labeled as useless, given an entirely new life cycle. If you've ever wondered what happens to old tires, or how we're turning environmental disasters into engineering triumphs, stay with me, because this journey will change the way you see waste forever. Let's start with a troubling reality. The sheer volume of tire waste has created some of the most severe pollution hotspots across the United States, Europe, and the Middle East. Massive storage sites that look apocalyptic from above. Dark landscapes of rubber decay. But here's where the story takes an unexpected turn. This massive volume of waste has triggered a breakthrough. A multi-billion-dollar industry called rubberized asphalt. And the numbers are staggering. Just 1 kilometer of road can reuse up to 10,000 tires. 10,000 tires that would otherwise sit in a landfill for millennia. But the benefits go far beyond just waste reduction. Roads built with recycled tire rubber are more durable, more resistant to cracking, and they reduce traffic noise by around 6 decibels. That's roughly half the sound level to the human ear. From a symbol of pollution, tires are emerging as one of the most promising sustainable construction materials of the 21st century. So how does this transformation begin? Every day, in the quiet, steady rhythm of modern cities, thousands of vehicle tires reach the end of their service life. At roadside garages, maintenance stations, and large-scale replacement centers, worn tires pile up. Most have exceeded safe limits for tread wear and load-bearing capacity. Left in nature, a single tire can persist for decades with virtually no decomposition, slowly becoming a long-term source of contamination. But from the recycling industry's perspective, each worn tire is urban ore. Inside every tire lies a complex blend of natural rubber, synthetic rubber, reinforcing steel, textile fibers, and chemical additives. Materials that, when processed correctly, hold significant economic value. Specialized trucks equipped with high-load platforms follow fixed routes, gathering tires from multiple locations. This prevents outdoor storage, where tires trap rainwater and become breeding grounds for disease-carrying insects. The logistics are precise, the system efficient. The recycling process begins with a critical challenge. Embedded inside each tire is a steel reinforcement ring, the bead that locks the tire firmly onto the wheel rim at high speeds. In recycling, this steel becomes the biggest obstacle. If not removed first, It can chip cutting blades, snap drive shafts, and halt the entire system. Workers feed tires into specialized bead removal machines. Inside, a hydraulic hook system capable of generating enormous pulling force digs deep into the tire bead. Using brute mechanical strength, it extracts the entire steel core in just seconds. The force is so intense that the thick rubber body violently twists and deforms during the process. Each heavy-duty truck tire yields around 2 kilograms of high-quality carbon steel. Once separated, these steel wires are compressed into compact bundles and transported to metallurgical plants, where they begin a completely new life cycle. Meanwhile, the remaining tire carcass, now far more flexible, is ready for the next stage. Section 4. Shredding. Rhythmic, methodical. Before mechanical processing begins, tires pass through high-pressure washing systems that remove mud, oil residue, and embedded gravel. This protects cutting blades from premature wear and plays a decisive role in maintaining production line stability. In the primary shredding stage, whole tires are fed into high-torque cutting machines. Slowly rotating alloy steel blades slice them into coarse fragments measuring several inches across. This low-speed cutting method minimizes heat generation, preventing the rubber from softening or sticking to the blades. The shredded pieces then move into secondary grinding, where their size is reduced even further. High-strength magnetic systems recover the fractured steel reinforcement directly from the material flow, turning it into a valuable stream of recyclable metal. The final output is crumb rubber with tightly controlled particle size, stable enough for classification and reuse. At this stage, the tire has completely lost its original form and becomes a raw material ready for new applications. Section 5. Precision sorting. Scientific, precise. All material passes through a multi-deck classification screening system. Particles that meet required sizes move forward, while larger pieces route back to the grinder. Among these outputs, the fraction ranging from 0.5 to 2 millimeters is especially critical. This is the exact rubber size used to produce rubberized asphalt. The precision here is non-negotiable. Too large, and the rubber won't properly integrate with the bitumen. Too small, and it loses its performance-enhancing properties. Quality control is constant. Samples are collected, measured, analyzed. The consistency must be perfect. Section 6. Preparation for asphalt. Chemical, transformative. After crushing and screening, crumb rubber still retains residual moisture, fine dust, and trace impurities. These interfere with how rubber interacts with hot bitumen, preventing the mixture from achieving the bonding strength required for high-performance pavement. The rubber granules are fed into rotating drying drums, large steel cylinders set at a slight incline and kept in constant rotation. Hot air, typically from natural gas burners, is introduced at temperatures ranging from 200 to 260 degrees Fahrenheit. As the material tumbles inside, moisture is gradually driven off. The surface of each rubber particle becomes dry and chemically active, ready to interact with hot bitumen. Modern facilities use temperature sensors